Yes, okay. So maybe let's start. Thanks for all of you to be here, and sorry for the delay. Yes, so I want to tell you about, to talk about the glass transition, and over the years I've been thinking about it with various colleagues. So the situation, okay, maybe let me introduce myself. So I'm working at EPFL, I'm heading the lab of the physics of complex systems. And in my lab, we are interested in a variety of systems which have this complexity. What we mean by this is that the energy landscape has many metastable states. And so one of the questions of this talk is, if you go down this landscape, for example, by cooling the system, where do you end up in this landscape, and what kind of barriers do you face? Because that will then control, the dynamics or properties you are interested in. And those questions, we work on them in granular materials. In fact, I talked about granular materials here a few years back. Also, when we think about plasticity of mayonnaise or things like that, and more recently, thinking about deep learning. I had actually a talk polished for you guys on deep learning, and I thought I was going to talk about this, but I was told, no, you have to really do physics. And it put me in the position of tell you about what I'm most interested in those days, which indeed are projects we are only now writing up and trying to expose it as a master student level. And so it's a challenge, but I think it's something fun. I think those ideas lead to, I hope, a different perspective on some of those questions. I also have to acknowledge there is a movie to make it more friendly, but apparently it's not going to work, the movie I was planning to show you, so sorry for that. Okay, so broad introduction. I think you all know what are glasses. In fact, it's a very old artifact. You find that 4,000 years ago, humans were doing beads of glasses, jewels. You also know that you do beautiful art with it. For example, stained glasses, vessels, and so on. And that we use it for technology, windows that were invented by the Romans already, so glasses that we wear, optical fibers, and so on. And many of the nice properties of glasses come from the fact that at a microscopic level, they are actually disordered structure. They are isotropic, and they don't have big defects like grain boundaries because they don't have this long-range order. And thanks to that, they cannot, diffract light and things like this. And so they can be nicely transparent. So in this talk, we're interested in the making of a glass, which you make from a liquid by actually quenching it. And the idea is you have to choose a good chemistry so that the crystal is not too favored, and then you rapidly quench the liquid, and at some point, the liquid becomes so slow that it starts to act as a solid. So now in this presentation, it's a field that has a very big field, and so there will be a lot to say about facts of the glass transition, and I decided just to stick to 2 facts. And the first one that you can study experimentally is the dynamics. There is a time scale that characterizes when you cross over from a solid behavior to a liquid, alpha relaxation time scale, where the stress decorrelates, the particles move by some amount of order of their radius, if you want. And experimentally, you can actually access to this quantity by measuring the viscosity of the liquid. And the viscosity is essentially G, which is a high-frequency modulus, times this time scale. And in experiment, you can measure this time scale by measuring this viscosity, for example, on many decades. I mean, that if it's very hot, it can, the frequency is terahertz, so 10 minus 12 seconds, until a scale of minutes. So you have more than 15 decades where you can actually study the dynamics. So this axis would be the log of the time as a function of inverse temperature. So when you cool the system, the dynamics slows down a lot. Okay? Then you define the glass transition when this time scale starts to be of order of the time scale of the lab. It starts to behave as a solid, but it's a purely engineering definition. It's not like there is a sharp phase transition there. Okay, so one way to think about what's going on is that there are barriers that particles need to move around in the system to relax. And so you can think about this relaxation time as some microscopic time scale times the exponential of those barriers divided by kT. And in some liquids that are called strong, actually this activation energy EA is constant, like silicate. It's essentially constant. But in other liquids that are called fragile, as you cool the system and you go down in energy, the barriers that you face become bigger and bigger. They can increase by up to a factor of 5 or something. And so one of the questions is really to understand, so those would be those curves here. So, okay, so I'm not that tall, sorry. But, if you have a strong liquid, actually on this plot, which is a log of time versus Tg over T, if it's strong, you just have a straight line. So silicate is, for example, the straight line over there. But those strong liquids, you know, they seem to slow down much faster. So why is it that they do that? What's causing this increase of activation energy? And that takes place while there is no obvious change in the structure. That's first fact. And then there is fact 2, and that's it for this presentation. So another fact is that if you look at what's going on in real space, you find that as you cool down the system, the dynamics becomes more and more correlated. And you can extract those correlation lengths experimentally. I'm not going to tell you how, but you can actually. But here, I'm just going to show you what you can do numerically. You can simulate liquids, not on 15 decades. And what is shown here is just the motion of the particles on the time scale, which is of order of this tau alpha. And what you find is that you have big patches where almost nothing happened. So it was still, if you want, a solid there, but other regions where it did relax. Okay, so you would really like to also understand those dynamical heterogeneities. One thing that's somewhat fascinating about this field is, despite the fact that we have access to, you know, movies of particles, we can simulate them and so on, as you will see in this talk, theories of the glass transition are very diverse, completely different, and we still do not really agree on what is a good theory. So for the purpose of this talk, it's actually useful to think about two kinds of theories. And normally they are not really grouped that way. So in some theories, actually it's easy to have local rearrangement of the particles. So you have some small barriers in the system. But what's really slowing you down is that to really relax, you need to break the system on some scale that grows. You need some cooperativity. So really in those models, the fact that the activation energy grows is very much related to the fact that I have some length scale that grows under cooling. And there are models that do that, and some can be very different. I mean, you have very different models that enter into this category, and I will just tell you that. And so for those models, it's very natural that, you know, I mean, the fact that the activation energy increases and that the dynamic is correlated comes hand in hand. But you have another viewpoint, a very old viewpoint, actually, which is rather that saying, well, liquids are very slow because moving anything, even a few particles around, is costly. So the activation energy is just that sort of local barrier scale. And you have theories that are like maybe 50 years old, like free volume, maybe somewhat more recent theories like elastic models. And those theories have not so much traction among theorists. I mean, there are some people who believe them, but I would not say it's a majority. And one of the reasons also is because it's not clear if you say that barriers, you know, local barriers control the dynamics, what is this correlation length? Okay, so in this talk, I will defend this picture. I'm just announcing the theme, so it's easier to understand. So, so let me just tell you a little bit more about those the different theories that enter in those different categories. So there is one view, which is that really underlying the slowing down of glasses, there is a thermodynamic phase transition. There is some kind of order that grows in the system. Now, this order is hard to detect. You need very astute ways maybe to detect it. But there is a structure that's growing in the material. Because of that, the dynamics become more correlated. That's just this length scale psi. And the barrier to break the system and relax is typically a Power law of this length scale. Okay? Okay, so that's one of those models where it's easy to relax a few particles, but you need to do something very cooperative to really relax. Now, there is a completely different class of model which is also cooperative, and they are called kinetically constrained models. And I like this sort of little picture to tell you what it's about. So maybe you've played this game, right? You start from a random order, and you need to order those squares in the right sequence. And you will need to do lots of motion to actually do it. So essentially, in those kinetically constrained models, you know, what makes it easy to move is to have those black squares, defects if you want. Well, in those models, typically these defects have some energy. And so if you lower the energy U, so if you lower the temperature, you have less and less of those black defects. So you have big region without defects. You have a length scale that grows, just the distance between defects. And in the most interesting model, the black square cannot move alone. They need other black squares to move. And so you have those big regions as you lower the temperature where you don't have any black squares, and they need to be invaded by a bunch of black squares together to relax the system. So in those models too, it can be very cooperative. So essentially moving one single black square is of order of the energy U I told you about, but you can have, to relax the system, you can have barriers that are much larger. Okay, and now comes the sort of very simple picture, which is the fact that actually local barriers matter. And here maybe let me illustrate it with the model that are called elastic models. So the idea is very simple. It's just saying on short time scale, a liquid is essentially a solid. So if I want to move some particles around, I will need to have some sort of plastic deformation in some volume V. And the magnitude of the plastic deformation, I will call it gamma. And then just from elasticity, you expect that this will cost you some energy that will grow like the elastic modulus, the volume times the strain square, something like this. Okay, so it's a very simple estimate. And then if you make the non-trivial assumption that this little volume V and the little strain gamma do not change with temperature, then you would predict that the activation energy would grow with the shear modulus in the system. And now there are more refined pictures of that, like Edan Lerner in Amsterdam. Now it's true that those two quantities appear to be quite correlated. So fragile liquids are also liquids that get actually quite stiffer under cooling. Okay? But here are some problems. I mean, is there a smoking gun? Can we give direct evidence that really local barriers matter? So that's the first point. The second point is, okay, but if this is local picture, then why do we have correlated dynamics? And the third point that I was planning to talk about, but it was too long, is why is it that in some liquids, you know, those barriers grow, or the shear modulus grow? So now I just want today to talk about those 2 points. Okay, so this is the menu. In the first part of 2 projects that we are writing up. So in the first part, I want to give what I think is a direct evidence that local barriers control what's going on and that you don't have this cooperativity, at least in the numerical classes that people commonly look at, which we'll also look at. And then in the second part, I want to tell you that even in models where, you know, local barriers matter, you can have very rich collective dynamics. And I want to propose a new view about those, what is this dynamics. Okay, so the first part, the idea is going to find a sort of smart algorithm to make this measure of local barriers. So what we have to think about is this energy landscape, if you want, the potential energy of this system of interacting particles. It depends on many variables. It lies in large dimension. And people have tried, I mean, I've studied it in the field. So for example, you take a model like this, you do a molecular dynamics simulation, and you try to look at rare events and relaxation and things like that. Here maybe is one of the latest recent papers. I mean, it was very active maybe 15 years ago. Essentially, all this work was done at large temperature. And okay, so it was at large temperature when the liquid had just relaxed by, a few decades. So in this talk, I will look at the liquids in, at lower temperature where it slows down more, where the kind of idea I'm presenting, I think, may work. At very large temperature, I don't think it would. And also, we're going to use a different method to try to think about the landscape. So the methods we'll use, and I will tell you it's used in other fields, we're not really inventing that, is to quench the system. So you take a liquid, you equilibrate it at some temperature, then you quench it to a minimal of energy, a local minimum, and then you do perturbation to study how you can excite the system and find new minima. And the way we're going to do it, because at the end we want to detect excitation, I will call them, that have a small barrier, we're going to use temperature. So you equilibrate the system, it's really equilibrated, you quench it, and then you do very small temperature cycle, and if there's too small, nothing happens. You go back, this configuration 1 at 0 temperature here and here are the same, you didn't jump over a barrier. But we look at the minimal cycle where, yes, something happened. In fact, we have algorithms that if two things happen at the same time, we can reconstruct it, and we really isolate independent events. Okay, so that's the concept. I will call it elementary excitation, the minimal rearrangement in systems like that. And in other fields like of the glass transition, for example, when people study low temperature properties of glasses or plasticity of amorphous solids, that's really the way they think about this. And so what you find if you do that are local rearrangement of a few particles, okay? In the energy landscape picture, along one direction, you jumped over one barrier, okay? So we pay attention that our algorithm just jumped over one barrier, actually. So it is a local rearrangement of a few particles, but it's also interesting to notice that it is an elastic medium. If you have a local rearrangement, it will have a far field response. The stress will decay as a dipole, like 1 over r, the distance to the dimension of space, and things like that. Okay, so we can identify those excitations, and then you have techniques. We use a string method to, once you identify those two states, to really measure what is the path in between them. I'm not going to describe that. Let's assume it's true. And then in real life, there is a characteristic time to jump, to relax an excitation like that. So a big difficulty in extracting excitations is that if you take a numerical system and you go at very low temperature to excite them, you will see the low energy ones, the few low energy ones. As you crank up the temperature, the low energy one, because their time scale goes exponentially in their energy, will start flipping hundreds of times before you see more interesting higher energy excitations. So you can only get a few excitations with a method like that because the larger energy ones are hidden by the super high frequencies that keep jumping around and screw your analysis. They hinder your analysis. Okay, so the key idea here in this first project is actually to introduce an algorithm that can deal with this problem. We gave it a name, we call it SEER, but at the end, the idea is very simple. I would have, okay, so I don't have a stick or something. No. Okay. Oh, that's good, thanks. Okay, so here's the idea. You take your system, you equilibrate it, you quench it, and then you excite it, and you find the first excitation. Let's say the lowest one was this. In a nutshell, what we do is that once we find it, we're going to heal this, to strengthen the system here, I will tell you how, so that nothing can happen there anymore. And then you continue cranking up the temperature, and so you will discover another one. And then again, you heal the system here, you strengthening it, and it cannot be, there is no problem there, and then you increase the temperature and you detect more and more of those excitations. So the way we do it is to have a minimal perturbation that can prevent this excitation to be reactivated. And here is the minimal perturbation. So imagine you have an excitation like that. in your phase space, only in this direction, so you're in large dimension, but in this one direction, you will add a parabolic potential whose strength is the minimal one that will make this excitation become like that. Okay, so then you have no more risk than, you know, this guy can go back. Once you discover new excitations, you study them in the absence of any external potential. Okay, so you can have access to the real thing with this. And then you crank up the temperature to discover more and more. Okay. So thanks to that, instead of just getting a few excitations, in one run, you can get hundreds of excitations. What we do to seek to be systematic, to have most of them, is that we don't just do one run, we do 10, 20, 50 runs. And every time we discover a new excitation, we put them in the library. And then you can measure a density of state, the number of excitation at some energy level. And so what you find is that at low energy, it converges. So it seems that you have access to all the excitation you could find in a range of energy. At large energy, no, we certainly have not converged, and those curves we should not trust. So at least for some hundreds of excitation, we can start to reconstruct an estimate of the density of state. Okay, now we can study how this density of state, which is here shown only in the region where we believe it, how it evolves with temperature. And so those different colors are different temperatures. This is actually rather large temperature, you know, and this is very slow. We use swap algorithm to equilibrate, very strong algorithm to equilibrate at very low temperatures. And so what you see is that as you quench a system, your density of excitation essentially creates a sort of gap. You don't find any excitation in a big range. Really, the key finding is that those curves, they are essentially collapsed just by a shift. Okay, here I just took those curves and added a constant, and they all look alike. And that's a key observation. Okay, this shift means it's equivalent to have all the excitation in your system increasing their energy by some quantity B of t that we can extract by collapsing those curves. Okay? Now, that's a powerful observation, because if you make an assumption that many in the field do not, those who believe in this cooperative model would not agree, but if you believe that the dynamics, if you assume that it's not cooperative, it's only governed by barrier, then this observation fixes the fact that the activation energy, when you change temperature, has to increase by this shift. Okay, you don't know what the absolute value should be, but you know how it should change. Okay, and okay, so that's maybe the slide to remember of this presentation, is that this is something that you can test without any fitting parameters. So what you measure doing molecular dynamics on those liquids is the relaxation time, and by inverting it, you can essentially measure what is the activation energy. This T0 is a macroscopic timescale. In fact, we even don't fit it. We can measure it independently, and I could discuss how at the end of this talk. And so as you cool the system, those points correspond to the activation energy measured from the dynamics. And in blue, you have our prediction. So you should, here we fit, we have an offset that we don't control. So this point here, you should not be impressed because we fit the two to be the same. But what really we do, which I think is rather remarkable, is that we can predict the change of activation energy without any fitting parameters. So we see strictly no trace of cooperative effects, at least in those liquids, which are the typical liquids that people study numerically. So just to put it into perspective, it's the same as saying that we can predict what is the dynamics as you cool down the system. I think it's interesting to tell you where we do this analysis. I was planning to tell you more on that, but when it's very liquid at large temperature, we don't think such analysis should work. Again, this point is fitted, so it's normal that those two look alike. But then we predict the change of the dynamics with this approach. Okay. All right, so that's the first part. It's this evidence that's somewhat surprising that we see no cooperative effect. But then it forces a question on us, which is, if it is the case, why is it that, the dynamics is correlated? And to discuss that, I will introduce some models that were actually Paris was, I think, a region on Earth where they were discussed and introduced a while back to think about plasticity of soft matter systems, actually. So in those models, you think about the material in a mesoscopic way. You cut it into boxes, and each box has a variable xi, which tells you about the stability in this region of space. Xi is just, okay, for those of you who do some mechanics, it's just how much stress should I add to the system to break it. It should be a tensor if it's stress, but you can think it in a scalar way, it makes no difference, okay? All right, and now you have a little dynamical rule. If one of those xi becomes negative, then this block is unstable. It's going to relax, rearrange, and to model that, you will pull another random variable xi that you will declare exist in that region of space. But also you have interactions. Because if this guy relaxes, it will, it's a plastic strain, so it will change the stress elsewhere in the material. So those different blocks are actually interacting. So they are interacting with some propagator Gij, which just essentially, well, depends on the distance between I and j, and also on, okay, it also has some angular dependence, so it's not clear here. But so this square relaxing changes stress elsewhere. What you need to remember is that this change of stress decay like 1 over Rd, like a dipole, essentially, but it's changing sign. Some regions are stabilized, other regions are destabilized. Okay? Those models are known to capture interesting aspects of plasticity. Some are observed experimentally. For example, avalanche type response. Okay? So let me try to tell you how that works. In a model like that, so imagine this is the axis x. All your blocks, they have a value, so you put them somewhere on this axis. If you're negative, you're unstable. And so if you're unstable, at the next time step, you will relax, and you will be sent somewhere at a positive value. When this happens, all the other sides are going to get a kick of stress, their stress value, and therefore their parameter xi is going to change. The sign can vary, and some will get small kicks because they were very far away from the block I. Some will get large kick because they were close to the block I. Okay? And so those kind of models display avalanche type response, because if one guy becomes unstable, then in response, other guys can become unstable, which themselves can trigger other instabilities, and at the end, you can have big events where many sites actually relax. Okay. Now, another point I need to make is that you can actually think about what is the distribution of stabilities. It's important to understand those materials. How many regions are about to fail? And what you find, this is the histogram of all those values x, is that close to 0, it vanishes with a non-trivial power law. And the physical reason is not too complicated. It comes from the fact that those sites, due to mechanical noise of guys failing, they do some kind of random walk. But for them, this is an absorbing condition. So if you had a random walk with an absorbing condition, you know that the concentration will vanish linearly close to this point. Here it's a bit more interesting because it's not really a random walk. I mean, the noise, I told you, you can have big kicks and small kicks. Actually, if you forget spatial correlation, then the model becomes essentially a Levy flight. So the mechanical noise is much better described by a Levy flight, which has very big jump and small, a few big jumps and very small ones. Now you can work out, how distribution of concentration of Levy flight walker act close to, a boundary, and you find that actually there is a non-trivial exponent. In mean field, if you really have Levy flights, this exponent theta is 1/2. And as you will see, it works not too bad in 2D, or as I will show you later on. Okay. Now, this system, you can also think about it, those kind of models, at finite temperatures. Essentially, what you say that those blocks, they can also have a barrier, and they can relax above those barriers. And EI is just the energy barrier of block I, which is just a function of the stability xi. If the stability goes to 0, then the energy should go to 0. And F should be an increasing function. You know, if you have large stability, you have a larger barrier. Okay, and then you postulate that a block I will actually relax with a characteristic time, which is just activated. So just the exponential of EI over KT. Now I will give you essentially two results. If you look at very low temperature, and you plot the density of excitation energy, it's really the same quantities I was extracting in the molecular dynamics simulation, as a function of E. When the temperature vanishes, this displays a gap and a power law just the same as before with the exponent theta. So let me try to give you an intuition for that. I mean, the intuition is that if you're at very low temperature, sites that have a smaller energy will relax much faster than sites that have a larger energy, right? Because it's an exponential dependence. So at very low temperature, essentially the dynamics is that of taking the weakest site and relaxing it. So imagine that you have a population of sites, you take the weakest, you reintroduce it there, and you give kicks to the other. Effectively, what it does is creating some absorbing condition. Those region is a dead region. As soon as you enter it, you will die. And here is our absorbing condition. And close to the absorbing condition, we have the same physics as before, and so we have this exponent theta. If you are at finite temperature, actually you have a small change. Instead of having a sharp gap, you have an exponential tail, but it's a small quantity on just on the scale of the temperature T. And what you find also is the dynamics in this model is just activated, and here enters the gap energy E star. Okay? So the key point I want to make, I think it's more made at the next slide, but you can already see it here, is that in those models, despite the fact that you have interactions between local excitations, it's still true that the dynamics is governed by local barriers, right? If you can measure N of E, you can measure E star, and you can deduce the dynamics from it. Now, in this model, it's a very simple model, and E star is actually not dependent on temperature. If you want, it's a model of strong glass. But that's because we're assuming that the property of excitations are always the same independently of temperature. Now, I told you real fragile liquids, for example, their shear modulus increases significantly under cooling. So if you want, the scale of elastic energy should increase. And so phenomenologically, E star should increase, right? So in this more realistic view, the density of state will actually shift with an E star that grows under cooling. Okay, so this is just to say that this is very consistent. Those kind of models are very consistent with the first finding I showed you in the first part of the talk. So if you put interaction between local excitation, you still have that local barriers control the dynamics. And now that's where, oh, the movie? Oh yes, the movie is there, okay. And now the key point is that in those models, you do capture interesting collective dynamics. And here's how people visualize it in a numerical glass. You can also do it with imaging in a real glass, but okay. So those are molecular systems where you do molecular dynamics. And at T equals 0, you color everything in blue. And if one region has relaxed, you color it in red. Okay? And what you see is some regions that essentially relaxed. It's a sort of coarsening process where they get bigger and bigger with time. And there is a characteristic scale of those dead regions where nothing happens, and that defines the correlation length I told you about. Those data are actually done at ENS, Misaki Ozawa and Giulio Biroli, simulating this model they find, okay, at least qualitatively, you know, a very similar coarsening. And, okay. And so in the few slides that I have left, so I'm happy that I actually prepared a very short talk, which I will explain you how we think theoretically. We think we have a theoretical understanding of how to describe those activation processes. So here is a physical picture in a model like this. So this is your density of excitation. So what's going to happen is that at some point you can have a fluctuation and you can thermally activate one of the excitation with the lowest barrier. Okay, so let's say this guy relaxes. Because it's relaxing, it's going to give kicks to the, you know, activation energy, or xi or e, the same, of sites that are around him. So some will, you know, go past this gap value here. So now those guys, they are not mechanically unstable. They still have a finite barrier, but they get activated by thermal fluctuation much faster than those guys here. Okay? So you can define a thermal avalanche considering the event or where you keep having sites below the gap value. And this will grow in time. And what would limit the size of those avalanches is the fact that elsewhere in the material, you also do nucleate other avalanches. Okay? So it's a competition between having one avalanche that grows and others that compete with you that actually fixes a length scale in those models. So in one slide, I'm telling you the idea of the theory that we have. And it's essentially finite size scaling. So the idea to determine this length scale is asking the following question. If I take a finite size system, at which temperature can I think about avalanche type response? If I can think about avalanches if the dynamics is like that. I take the weakest site in my system, it gets activated, then it does its business, it creates a thermal avalanche, then it stops, and then I start a new activated process from here. In this limit, you can really define avalanches. But in your finite box, if the temperature is too large, you cannot think like that because there is competition. There start to be a bunch of states that can nucleate something. So it means there is activity going on in parallel, and you cannot think about avalanches. Now, it's very simple to write what is the criterion that, you know, what is the temperature or the system size for which you go from a regime where you always activate the first one to a regime where you have plenty of them activated. And it's just governed by this exponent here. And so what we find with this argument is that the correlation volume should go like should explode at vanishing temperature with this exponent theta that characterizes this singularity in the density of state. We can measure theta to be 0.65. It's not too far from the mean field value 0.5. This is a theoretical prediction. And in those models, it's also from the dynamics, from those movies I showed you, we can also measure this characteristic number of particles that are involved in the correlation at finite temperature. Okay, so we can also measure that. And this is called chi4, but essentially think of it as a correlated volume of the dynamics, and the theory works well. So at least for this system, we think we have the essence of what's going on. So maybe the take-home message is that so many theorists in the field, we think about collective dynamics and barrier being really controlled by the same phenomenon. Here, what I'm showing you is that even though the activation energy is just controlled by elementary excitations, as in those models, you can still have a very rich dynamics, correlated dynamics. Okay. So I could have told you about, I had a part 3 that I removed, and in fact, maybe I would have had time for this. But I'm going to already conclude. Okay. So the first result is that at least for those numerical glasses, okay, so now there is a question of universality and so on, but at least for them, there is this quite direct evidence that the dynamics is governed by local barriers, and we don't see any trace of cooperativity. This is not, part two, this is not in contradiction with dynamical heterogeneities, because if you couple those local excitations, you get those heterogeneities. And that suggests a new picture for correlated dynamics, really as thinking about thermal avalanches. And there have been thought about thermal avalanches in the deepening, in other problems in physics, actually. Part three that I wanted to tell you about is the question of, yes, but why is it that the activation, those barriers grow in energy as you cool the system? And for elastic models, it's just saying, it's because the shear modulus increases and so. We think there is much more physics behind that, because we see that not only the energy of the excitation change, but also their geometry. Okay, this is essentially discussed in this paper. So, okay, if someone is interested, you can look at that. And it also makes a direct connection with mean field views on the glass transition. But, okay, I could take question on that, but I don't think it's worth entering it. So I would just like to now thank my collaborators. Unfortunately, I could not talk about the work with Carolina and Chris. So the work on identifying, local barriers in systems is done with Massimo and Wencheng. And the work on those elastoplastic models is done with Giulio and Misaki that you all know here. Marko Popovic, a former postdoc who is now group leader in Dresden, and his student Ali. And I'm done. I can take questions.